So the do now wanted you to just predict the pH, just a range, not calculate it, just predict. So remember that any titration is always an acid-base neutralization reaction. So we know that for each titration, we have to have an acid and we have to have a base. Well, if you look at NaHCO3, you're like, I don't know what that is because it looks like a salt. Switch over to NaOH. We know that NaOH is a strong base. So if NaOH is a base, that means that this must act as an acid. Our focus here is actually just on HCO3 minus because Na plus is always a spectator. Now, HCO3 minus is not one of the 7 strong acids, so this would be a weak acid, strong base titration. If it's not strong, it's not at 7. The pH is not at 7. So we have to think about where would the pH be. Now, kind of a shortcut, if you want to do it quickly, a shortcut is to just look at what is stronger. Because whatever is stronger actually will tell us the pH at the equivalence point. So what I mean by what is stronger is since we have a strong base, pH will be greater than 7. So the pH is going to be somewhere greater than 7. Now, the reason is not because it's a strong base. Please don't put that as a reasoning. That's just a shortcut. The reasoning is because of the salt that is formed. If we actually look at what happens in this, and this is a little bit weird because we're really focusing on HCO3 minus and OH minus. We actually get CO3 2 minus and H2O. CO3 2 minus is a weak base. So since the salt that is formed is a weak base, the pH is basic at the equivalence point. If we look at number 2, we have NH3 and HCl. I know HCl is a strong acid because we work with it a lot. NH3, remember NH3 is ammonia. It's one of the most common weak bases. So again, a shortcut is to look at what is stronger. So since we have a strong acid, we would expect the pH to be less than 7. Now our reasoning is not because, well, we have a strong acid. Our reasoning is because when we actually look at the salt that is formed, we form NH4 plus because the acid donates its proton, and Cl minus. Cl minus is neutral. NH4 plus is the conjugate acid of NH3. So after the neutralization, we form a weak acid. Doesn't matter that it's weak, it's still an acid. The pH is still less than 7. So the salt is always what determines the pH. And then finally, for number 3, KOH and HBr, strong base, strong acid. The pH of any strong titration, no matter what, is 7. Because the salt that is formed is KBr, right? And water. Water's neutral. K plus is neutral because it comes from a strong base. Br minus is neutral because it comes from a strong acid. So since the salt is neutral, the pH is 7. So the do now really just wanted this, right? Where's the pH range? But it's important to remember that the salt is what determines the pH. Any questions on the do now? All right, so we're going to go ahead and switch over. We will be in the practice packet. So in the practice packet, same packet that we worked through yesterday, the very last page, page 15 and 16, we have the weak strong titrations. Now, I'll keep this for you. I'm going to write a little bit bigger. So I went on a couple pages for each question. If you tend to write bigger and you don't want to like squish everything in, then just have like an extra piece of paper that you can kind of add to the back of the practice packet. because the second question is actually on the back of this page. Number 1 is going to take us a little bit longer because it has 2 like volume to volume questions. And then number 2, hopefully we'll get through a little bit more quickly. So these are the questions these are the notorious titration questions, but we're going to work through these questions, and I'm going to work through it up here. I'm going to write extra information on the side. You don't have to write the information if you're like, I don't need that. So for this question, it says 45 milliliters of 0.1 molar NaOH is added to 50 milliliters of 0.1 molar acetic acid. So I'm going to start by just thinking about what this is telling me. Here's my acetic acid information. So I'm going to think about what's in the beaker. That's really important with titrations. So it tells me that in this beaker, in this container, I had 50 milliliters of 0.1 molar acetic acid. So I had 50 milliliters of 0.1 molar HC2H3O2. And then from the burette, we added 45 milliliters of 0.1 molar NaOH. And so with this, the first thing, you can see that there are 5 different things that we have to do here. So once it's calculate the initial pH, sketch the titration curve, add specific points, calculate the pH of the solution formed, pick the indicator, calculate the pH of the equivalence point. The 2 pH calculations are what will take us the most time, because that's the neutralization where we add volume to volume. So we have to do dilution, stoichiometry, equilibrium. But the first thing that I want to think about is calculating pH. So I'm going to write this down the side of the page. And so thinking about calculating pH, we have 4 main areas that they might ask us to calculate pH. The first is the initial pH. So the first thing they might ask us to do is calculate the initial pH. Well, for the initial pH, we just think about what's in the beaker. So in this case, in the beaker, before any NaOH was added, we had a weak acid. So that means I can use Ka and equilibrium. We've calculated the pH of a weak acid. You have a weak acid, anything that's weak exists at equilibrium. Anything that's weak exists at equilibrium. The second place, and we'll do it in this question, that they'll ask us to calculate pH is between initial and equivalence point. So they might ask us to calculate the pH somewhere between when the first drop of NaOH is added all the way up until the equivalence point. So this is a buffer region. So we can think about it as a buffer. So what we need to do is figure out what we have, and we can use the buffer equation. So we'll say look at neutralization and use the buffer equation. So this will help us review buffers too. The third place, and you will see a pH at the equivalence point question on the quiz, at least one. Yes, it's multiple choice, but you'll still see one of them. So at the equivalence point, so what's important to remember is that the salt determines the pH. The salt determines the pH. So the pH at the equivalence point is based on the conjugate. So I'll say all acid and base has been neutralized. And the pH is based on the hydrolysis of the salt. So if the salt is neutral, then there's no hydrolysis, right? The pH is 7. There's no calculation needed. But in the weak strong titration, the pH is not 7. So we look at what is happening, what part of the salt is affecting the pH. And it's going to be a weak base or a weak acid, and so it exists at equilibrium. And then the final place is after the equivalence point. And so after the equivalence point, pH is based on excess. H plus or OH minus from the titrant. So that's just stoic. Figure out how many moles of excess we have. And then you just find the molarity, take the negative log. So we have 4 main places, right? We kind of have this down the side just to help us. We're only going to write it one time. And so for this, the first thing that it wants us to calculate here is the initial pH. So for the initial pH, we have to think about what did we have in the beaker initially. So if I come back up to the top, in the beaker initially was just acetic acid. So I'm going to just label this initial pH. And if you need to go back and you need to look at like my work or anything, I have this scanned in. And what I'll actually do is I will link like my work to the practice video as well. And they'll be on the practice playlist. And you can also find this on the website. So for the initial pH, the only thing that we had in the beaker initially was acetic acid. Yes, we had water as well. I'm going to neglect water. I'm going to use the simplified version. So we have acetic acid. Anything that is weak exists at equilibrium. No matter what, weak acid, weak base. If it's weak, it exists at equilibrium. So it exists with its ions. Now, because this is at equilibrium, this will have an equilibrium constant, some value of K. If it produces H plus like this, it's Ka. Now, on a test or a quiz, you will be given the Ka values. For this, we weren't given it. You could look at Appendix D for the Ka of acetic acid. I'll tell you what the Ka is. The Ka of acetic acid is 1.8 times 10 to the negative fifth. We use acetic acid so much. Acetic acid's Ka is 1.8 times 10 to the negative fifth. You can find that in Appendix D. On a test or a quiz, you would be given any K values that you would need. Now, if we want to calculate the pH, that means that we need to find H plus, but we need to find H plus at equilibrium. Because remember, pH and pOH are at equilibrium. So any calculations that are required of anything weak needs an ice table. Initially, we had 0.1 molar acetic acid. We didn't have any H plus or any acetate in the beaker initially. We just had the acid. Now this looks like an ice table that we've done before. My goal is to solve for H plus at equilibrium. So minus x plus x plus x, 0.1 minus x. And so I can write my Ka, so 1.8 times 10 to the negative fifth is products, so x times x over 0.1 minus x. So x squared over 0.1 minus x. And then to prevent the quadratic, I can assume x is small. That allows me to ignore this minus x. And so I could do 1.8 e negative 5 times 0.1, multiply the 0.1 over, and then take the square root. 0.00134. Then think about what x is. X is H plus, so I'm just going to label this H plus concentration, just so I have things labeled. Because now it helps me. If I take the negative log of this, I'm taking the negative log of H plus. So what is that? pH. So if I take the negative log, 2.872. So initial pH, we just had the acid in the beaker. So we were just finding the pH of a weak acid. You always just need to think about what is in the beaker, what is affecting the pH. If it's strong, you don't need equilibrium because it's a single arrow, goes to completion. If it's weak, it exists at equilibrium. So the next thing says, sketch the titration curve and add specific points. So I'll go ahead and label the next part, titration curve. So I know that for the titration curve, I want to start the curve with my y and my x-axis. My y-axis is pH. My x-axis is volume added. And in this case, since it was NaOH, it was in the burette, in the burette, it's going to be volume NaOH added. You guys will actually be doing a titration on Thursday, and you're going to be adding NaOH from the burette into the container, into the beaker below. So we start with our axes, our x and our y axis. We just calculated the initial pH. So we know where we should be starting. Just put a dot here. 2.872. So my initial pH, 2.872. And that's all we really have right now. So I'm just going to draw a general curve, what it looks like. So I know that I'm going to have this buffer region because it's weak strong. Then it will go up and it will plateau. Something kind of like this. So here's the volume at the equivalence point, pH at the equivalence point. We don't know that yet. I'm just going to put a dot on here, but we don't know what the actual value is yet. We don't know the volume yet. We're about to figure out that. And then we also have another important point. Because if I go to half of the volume at the equivalence point, Half of the volume at the equivalence point is the half equivalence point. What is important about the half equivalence point? What is pH equal to? pKa.
Oh, that's performance.
So at the half equivalence point, pH equals pKa. Now you might say, well, I don't know what the volume is at the half equivalence point. No, but we can figure out what the pKa is because we just use the Ka above. So if I take negative log of the Ka value, 1.8 times 10 to the negative fifth, taking the negative log of Ka is pKa. Negative log of 1.8 e negative 5 is 4.74. So at the half equivalence point, right here, the pH is 4.74. I'll kind of follow it up here just to make it. Half equivalence point is important because pH equals pKa. That is where the weak acid is equal to its conjugate base, part of the buffer region. So we labeled initial pH. Now, if this is a strong base, weak acid, where would we expect the pH to fall, just in general? Above 7. So this pH at the equivalence point should be somewhere above 7. So I'll just write that here. Equivalence point pH greater than 7. We don't know what it is yet, but we know it should be above 7 because it's the strong base weak acid produces a basic salt. Now, the volume at the equivalence point. I'm going to show you a quick way to do this if the molarities are the same. You can actually figure out using stoichiometry because remember at the equivalence point moles of acid equals moles of base. So we could use, I'm just going to go up to the top really quick. I could say, okay, I know in the beaker I had 50 milliliters of 0.1 molar acetic acid. I could use this to figure out how many moles of acetic acid do we have. Here's the molarity of NaOH. If I know that moles of acetic acid equals moles of NaOH, I could use moles of NaOH, molarity of NaOH to figure out the volume needed at the equivalence point. But because they are both 0.1 molar, the volume of NaOH is 50 milliliters. The volume of NaOH needed at the equivalence point is 50 milliliters because since they are the same molarity and the same moles, because that's the definition of equivalence point, they have to be the same volume. So whatever volume of acid we had in the beaker, we need that same volume of NaOH to be added to reach the equivalence point. So now I know that this down here is 50 milliliters, which means the half equivalence point is at 25 milliliters. So that's what we have on our titration curve so far. We were able to do initial pH, the half equivalence point, and figure out the volume of NaOH. Now, if the molarities weren't the same, then you just use the molarity equation for the acid, figure out how many moles of acid are in the beaker. At the equivalence point, moles of acid equals the moles of base that are being added from the burette. And then you use moles and molarity to go to volume.
Wait, so cool. If the molarities weren't the same, could we do like 45 milliliters times 1.1 and then divide?
Oops. So you would have to use if you want to use the MAVA one,
yeah.
Yes. But this amount of NaOH that was added, this does not say that it's at the equivalence point. So our goal is actually to figure out what do we need instead of 45?
Okay.
But you also could use MAVA equals MBVB because that works at the equivalence point when you're looking for molarity or volume. Yes. So now the next question says, calculate the pH of the solution formed. So we don't know if we're at the equivalence point yet. And based on what we just said, we know that it takes 50 milliliters of NaOH to get to the equivalence point. So we're actually, in this solution that we're forming, we're like right here on the titration curve. So I'm going to label this, calculate pH of solution. Now, here's what we want to think about. We're going to go back to the neutralization discussion that we had a couple weeks ago when we talked about what happens if you add an acid to a base, if you add volume to volume. So I'm just going to make a little note right here. We are adding volume to volume. When you are adding volume to volume and you have an acid and a base reacting, we need to go through those 3 steps. We're diluting the concentrations, we look at the stoichiometry involved, and we look at equilibrium. So the first thing we look at is dilution. So to calculate the pH of this solution, we want to figure out, our goal is to eventually figure out what is the pH. But when we mix these 2 solutions together, we're changing their molarities. So since we're adding volume to volume, we want to start with the dilution. So I'm just going to kind of label it like this. NaOH, I'm going to almost just put it in a table. Acetic acid. So here was their initial molarity. And then molarity after mixing. So NaOH had a molarity of 0.1 molar. Acetic acid had a molarity of 0.1 molar, but that was before they were mixed together. Dilution is M1V1 equals M2V2. So let me write this up top. So M1V1 equals M2V2. NaOH was 0.1 molar, but if you look up at the top, there was 45 milliliters of NaOH. I want to find the new molarity when these 2 solutions were mixed. So we had 45 milliliters of NaOH and 50 milliliters of acetic acid. So the new volume is 90 milliliters. Nope, can't add 95. 95 milliliters. This 95 is because we had 45 from NaOH, 50 from acetic acid. So what we're doing right now is we're figuring out what are the molarities of each of these right after we mix them together, but right before they react. Divided by 95. So here we have 0.0474 molar, so that's NaOH. I'm going to do the same thing for acetic acid. We have 0.0526. If we were at the equivalence point, these would be equal. If we were at the equivalence point, these would be equal. But we're not. So these are important because we can use these directly in our stoichiometry. Because now, so what we're doing is we're figuring out how are we changing these concentrations when they're mixed together? Because you're adding volume to volume. The next step in finding the pH of a solution when you're mixing two things together is looking at the stoichiometry. We're looking at the stoichiometry, so we're looking at the neutralization. So in this, we have NaOH reacting with acetic acid. Stoichiometry is just a single arrow. Neutralization is a single arrow. It goes to completion if possible. So one of the products is the salt. Na combines with acetate, C2H3O2. And then we have water. So I'm going to use these molarity values. I'm just going to write them directly underneath. Right, this is stoichiometry. Will one of these run out before the other? Yeah, which one?
NaOH.
NaOH. So NaOH is our limiting reactant. It runs out first. We are going to use NaOH up completely. So I'm just going to subtract just so we can see how it gets used up. If I use NaOH up completely, NaOH and acetic acid are a 1-to-1 ratio. So I'm going to use up the same amount of acetic acid. Oh, water we're going to ignore. If I'm using up the same amount of acetic acid, they're all 1-to-1-to-1 ratios. I'm also creating products. Now this is stoichiometry, so I've talked about this being called a BCA table before. Don't even need to give it names. B just means before the reaction, C means the change, A means after the reaction. It looks very similar to ICE tables. It's just another way to represent stoichiometry. So if I do 0.0526 minus 0.0474, I have 0.0052 molar and 0.0474 molar. So after the neutralization reaction, here's where I want you to think again. After this neutralization reaction, in the beaker, we have acetic acid and sodium acetate. So in the beaker, we have HC2H3O2 and NaC2H3O2. After the stoichiometry, if you still have something left in the beaker and it's weak, you have to think about equilibrium. Because acetic acid is weak and sodium acetate is weak. Really, we're focusing on acetate. We have to go to equilibrium. So I'll go to number 3 up here. Now, this is unique. Because if you think about where we are on the titration curve, I'm just going to come up really quick to our titration curve. We're right here. We are in the buffer region. We're in the buffer region here. So there are 2 ways that you could solve this. I'll put it in parentheses. You could use an ICE table, or you can use the buffer equation. You could use an ICE table, or you could use a buffer equation. We're going to look at using the ICE table when we look at the equivalence point. If you're asking what would the ICE table look like, well, you have a weak acid. So you would write the weak acid at equilibrium, and you have a common ion. You could add that common ion in. I'm going to use the buffer equation just so we can review the buffer equation because we haven't seen it in a while. The buffer equation is the concentration of H plus equals the Ka of the acid part of the buffer, and it's the concentration of the weak acid over the concentration of the weak base. So in a buffer, you always have a weak acid and a weak base. If you're looking and you say, how do I know this is a buffer? Well, here I have a weak acid and its conjugate base. A buffer has to have a weak acid and a weak base. So the H plus concentration, Ka is 1.8 times 10 to the negative fifth, because that's the Ka of acetic acid. We've used it twice already. The acidic portion of the buffer is acetic acid. Here's our concentration of acetic acid, 0.0052. The basic part of the buffer is the acetate ion. Remember, sodium is just a spectator. So 1.8 E negative 5 times 0.0052 divided by 0.0474. So my H plus concentration, 1.97 times 10 to the negative sixth. The goal of this part was to calculate the pH. If I have H plus, how do I find the pH? Negative log 5.70. So calculating the pH, when you mix two solutions together, you have to go through dilution, stoic, equilibrium. Now the next part says, select the best indicator. Now, if this were a test or a quiz question, you would be given a list of indicators. All right, and on here, you weren't given the list. If this were a test or a quiz, I would give you the indicator list. So I'll just label this best indicator. So just to review indicators, remember that we want the indicator to change color when pH equals pKa of the indicator. So change color when pH equals pKa at equivalence point. Okay, well, we don't know what the pH at the equivalence point is. So we'll actually go to the last question and then come back to this. So I'll just write this for now. pH at equivalence point equals. So I'll fill that back in and then we'll come back to it. So the very last part of this question says calculate the pH at the equivalence point. So pH at equivalence point. Calculating the pH when you add two solutions together requires you to go through dilution, stoichiometry, and equilibrium. So we need to go through what are the new molarities, what happens with the stoichiometry, what's formed, what's used up, what do we have left over in the beaker, and then equilibrium. So let's just start, again, like we did before, with looking at the dilutions. So I had two solutions. I had acetic acid, I had NaOH. Now these dilutions are not the same as what we calculated before because now we're at the equivalence point. So here I'll put before and then after we mix. So if we think about what we have, we might have to refer back In the beaker, we had 50 milliliters of 0.1 molar acetic acid. We are now at the equivalence point. At the equivalence point, it required 50 milliliters of 0.1 molar NaOH. NaOH concentration was 0.1 molar. If you look back at the titration curve, we said because the molarities were the same and the moles needed to be the same, the volumes were the same. So before mixing, this was 0.1 molar. We're going to use M1V1 equals M2V2 for dilutions. So acetic acid was 0.1 molar. We had 50 milliliters of it. We want to find the new molarity when we add the two solutions together. We add the two solutions together, we have a volume of 100 milliliters. So 0.1 times 50 divided by 100, 0.05 molar. Notice when you dilute to double the volume, the concentration gets cut in half. We do the same thing for NaOH, 0.1 molar. We have 50 milliliters. We're looking for the new molarity when we mix the two together. So 0.1 times 50 divided by 100. So it started at 0.1. After we mixed them together, but before they reacted, we had 0.05 molar of each. Notice how they're equal because we're at the equivalence point. So now we found the dilution. After you find the new molarities, after you mix the two together, we look at the stoichiometry. Because the stoichiometry, we're looking at the neutralization. So I'm going to write the reaction. I'm going to write the neutralization reaction that is occurring. I'm writing the molecular, so I'm not ignoring spectators. If you want to ignore spectator ions, you can. That means you would be ignoring the Na+. So NaC2H3O2 and water. So this is the neutralization reaction. Neutralization is an acid plus a base makes a salt and water. I know that I have 0.05 molar of both of these. So right after I mix them together, but immediately before they react, I have 0.05 molar of each. I don't have any products because this is the stoichiometry problem. So all we have was the acetic acid and the sodium hydroxide. Is one of these limiting?
Yes.
Right. Yes and no, right? They're co-limiting. They run out at the same time. So I'm going to use up, it doesn't actually matter which one you pick. So I'm going to use up all of this. 1-to-1 ratio. I use up all of the sodium hydroxide. But it's stoichiometry, so you're using up reactants and you're forming products. Again, if you think about the stoichiometry, if you want to put a name to each row, we call them BCA. It's just like an ice table, but you're not at equilibrium. You're looking at the stoichiometry instead. So I am out of my acid and base completely. The definition of the equivalence point is when the moles were equal, so they are completely neutralized. But now in the beaker, we have sodium acetate, and we can ignore water. If you put 0.05 molar for water, that's fine. It's a liquid, so it's not going to be included in anything. You have water in everything. So now in the beaker, I have sodium acetate. So I have this in the beaker after neutralization. Remember that the salt determines the pH. So let's take a look at this salt. We have NaC2H3O2. This technically breaks apart. It's a soluble salt. Will Na plus affect the pH? No, Na plus is neutral. Will acetate affect the pH?
Yeah.
Yeah, because acetate is the conjugate base of acetic acid. Acetic acid is a weak acid, so acetate is a weak base. So after the stoichiometry, we have the salt. The last part, when you're looking for the pH at the equivalence point, you're looking at how the salt affects the pH. So here we're focusing on equilibrium. All that's in the beaker is the weak base and water. Now, yes, Na plus is in there as well, but it doesn't affect the pH. So in the beaker, we have this weak base, C2H3O2 minus, and H2O. This is a weak base. It's weak. It exists at equilibrium. So it gets the double arrow. This is a base. It accepts a proton. Water donates the proton and becomes OH minus. So if this is at equilibrium, right, so this should have an equilibrium constant. If it produces OH minus, what K should it have?
B.
KB. And we know if we have to do calculations that we'll do an ice table. So we said that the only thing in the container is acetate and water. Because acetate is a weak base, it exists at equilibrium. So any calculations at equilibrium require an ice table. So the only thing in the beaker was acetate. So that's going to actually be our initial concentration. In the beaker, right after neutralization, we don't have any acetic acid or any hydroxide because it's gone. It was completely neutralized. And so now we can go through this ice table. We don't have anything else. We'll use X's. But here's where we have to be careful. Because when I plug this in, this is KB. Well, if you try to find KB for acetate in Appendix D, you're not going to find it. But remember that acetate is the conjugate base of acetic acid. And for any conjugate acid-base pair, Ka times Kb equals Kw. We know the Ka of acetic acid. It's 1.8 times 10 to the negative fifth. We can solve for Kb because Kw is 1 times 10 to the negative 14. So 1 e negative 14 divided by 1.8 e negative 5. Kb of acetate is 5.56 times 10 to the negative 10. I'm just going to underline it because that is our K value. In order to solve for the equilibrium row of this ice table, we need Kb. Because if I do products over reactants here, if I do acetic acid times hydroxide over the acetate ion, that is Kb because of the hydroxide. So now I have the value of Kb, 5.56 times 10 to the negative 10 is x times x over 0.05 minus x. Make a note up here, assume x is small. Now we can solve for x. So 5.56 e negative 10 times 0.05, multiply the 0.05 over. and then take the square root. X is 5.27 times 10 to the negative 6. Now take a second to think about what is X. So if I look up at the ice table, think about what might be useful if I eventually need to get to pH. Well, X is OH minus. You have two ways you could solve to get to pH. I'm going to do POH and then pH. You could do H plus and then pH. Using H plus times OH minus is KW. But I'm going to take the negative log of this. When I take the negative log of this, I'm taking the negative log of OH. So that's giving me POH, which is 5.278. And then 14 minus POH gives me pH. So the pH at the equivalence point was 8.722. When you are calculating the pH, when two solutions are mixed together, you do dilution, then stoichiometry, then equilibrium. If it's strong, you just do dilution stoichiometry, because then it 100% dissociates, so whatever you have will let you find the pH. But if it's strong, weak, you have to take into account equilibrium at the end. So if we come back up to the indicator part of the question, the pH at the equivalence point is 8.722. So we need to find an indicator that has a pH range around 8.722. Well, oh, you can't see that. There we go. pH range should be around 8.7. Well, the one indicator that we use a lot, actually I have it right here, is phenolphthalein. Phenolphthalein actually has a pKa of 9, so its range is 8 to 10. So the best indicator is phenolphthalein. Again, the Ka, I would give you the Ka. Ka is 1 times 10 to the negative 9, so pKa is 9. That means the range is 8 to 10. So that is the first question. Yes?
How'd you know it's phenolphthalein if you didn't know it was?
Well, so they would have to give you a list of indicators.
Oh, okay.
So in this, they would give you kind of like in the example that we looked at before, they give you 3 indicators and they say which one would be the best. So you want to find the one that has the pKa closest to the pH at the equivalence point.
Will they give us the Ka?
Yes.
Okay.
More than likely, they'll give you a list of Ka, so then you just take the negative log of those, and then,
All right.
yep.
That's all. Thank you.
Any other questions on this one? Yes, so Kw is from the equation sheet. So Ka times Kb equals Kw is on the equation sheet. Kw is the constant, the autoionization constant of water. As long as you're at 25 degrees, which we assume we are, Kw is 1 times 10 to the negative 14. I know also that, yeah, this makes your brain hurt. Yeah. Mm-hmm. It's long. It's long.
It was good
until you have to.
Thing.
Yeah.
Yeah.
So then we'll take a look at number 2. So number 2 isn't quite as long. We just have one of the pH at the equivalence points. So number 2 says 29.28 milliliters of 0.1032 molar acetic acid is titrated to the equivalence point. To the equivalence point with 25 milliliters of aqueous sodium hydroxide. So now we know these are the amounts that are needed to reach the equivalence point. So if I think about this, so I have my burette and I have my beaker. In the beaker was 29.28 milliliters of 0.1032 molar acetic acid. In the burette, to get to the equivalence point, we used 25 milliliters of NaOH. That was all it told us about NaOH for now. So the first thing for number 2 says calculate the initial pH. So calculate the initial pH. So I'll label this initial pH. So initial pH means before any of the sodium hydroxide was added. So think about what is in the beaker. The only thing in the beaker before sodium hydroxide was added was acetic acid, a weak acid. So we add acetic acid in the beaker. Because it's weak, it exists at equilibrium. If you want to say acetic acid plus H2O and it produces H3O plus acetate, that's okay. This is just a shortened, simplified version. So initial pH. I'll just make a note here. This is only weak acid. So use Ka and equilibrium. So I know that I have something that's weak and I'm going to need to do a calculation. We add 0.1032 molar acid, 0H plus 0 acetate. All we had was the weak acid initially. Now that's all it gave us, but it tells us that we need to calculate pH. So that means I need to find H plus at equilibrium. That's my goal. Because if I know H plus at equilibrium, I can find pH. So I'll go ahead and use X's. And I know that to plug this in, I'm using a K. Because it's producing H plus, it's Ka. Now we would be given the Ka of this, but this is acetic acid, so it's the same Ka we just used. 1.8 times 10 to the negative fifth. Ka you can find in Appendix D if you are not given the value. On a test or a quiz, you will be given the values that you need. You'll be given Ka, but might need to find Kb. So I know that Ka is products over reactants. So X squared, X times X, over 0.1032 minus X. I can assume X is small. So 1.8 E negative 5 times 0.1032. Take the square root. 0.00136. And I know that X is H plus, so I'm going to just label that. Once you know H plus, how do you find the pH? Take the negative log. Uh, 2.866. And then you can ask yourself, does that make sense? Does it make sense that the pH of a weak acid is 2.866? Yeah, as long as it's below 7, it's an acidic pH. So the second part of this is, what is the molarity of NaOH? What is the molarity of the NaOH? There are two ways that you can solve this. Either way works. Remember that at the equivalence point, moles of the acid, so moles of acetic acid equals moles of the base, so equals moles of hydroxide. So I know the molarity and the volume of acetic acid that was in the beaker at the equivalence point. I can figure out how many moles of acetic acid there were in the beaker. Remember, molarity is moles over liters. So if I solve, there are 0.00302 moles of acetic acid in the beaker, which means at the equivalence point, we need an equal number of moles. So that means we have an equal number of moles of NaOH. The problem told us that it took 25 milliliters of NaOH to reach the equivalence point. So if we have moles of NaOH and we have liters of NaOH that was required, we can figure out the concentration. 0.121 molar NaOH. Now you could have also used, because it's at the equivalence point, you could have used MAVA equals MVVB as well and gotten the same thing. Because the idea that the moles are equal at the equivalence point is why this shortcut works. But this shortcut only works if you have one H to one OH. So I mean, like HC2H3O2, that has one H plus at the beginning. NaOH has one OH minus at the end. So the shortcut works if it's one H plus to one OH minus. So either one of those works. Now, pH at equivalence point. So here's the longer of the questions. So again, pH at the equivalence point. Remember that we are adding volume to volume. What that means is we're adding two solutions together. When you're adding two solutions together and you are trying to find the pH, you have to go through the 3 steps. So the first is taking into account the dilution. So take into account the dilution. What does the molarity of acetic acid become? What does the molarity of NaOH become? So HC2H3O2 and NaOH. So here's before we mix and after we mix. Now in before, I'm going to put both pieces of information. So we had 0.1032 molar. We had 29.28 milliliters. Just to help us so we can see what volume we had and what the concentration was. NaOH. Well, we just found what the concentration of NaOH, what NaOH was. 0.121 molar. And the problem told us that it took 25 milliliters to get there. The reason I'm putting that in there, I'm just putting it somewhere to be able to use that information. So remember, for dilution, we use M1V1 equals M2V2. So M1 for acetic acid, 0.1032 molar. The volume was 29.28 milliliters. I'm looking for the new molarity when these two solutions are mixed. So the new volume is when the two are mixed. So that becomes 54.28 milliliters. So 0.1032 times 29.28 divided by 54.28, 0.0557 molar. So when we mix these two solutions together, right before they react, acetic acid's molarity drops to 0.0557. Do the same thing for NaOH. Notice how the V2 for both is the same. That's the new total volume. So the new molarity of NaOH, 0.0557. Notice they are the same because we are at the equivalence point. As you do more of these, you might start to realize, okay, if I'm at the equivalence point, I can see that I have both of the acid and the base get used up and I form the same amount of salt. These numbers are what are important for us to look at the stoichiometry. So if I look at the stoich, I have acetic acid plus NaOH. The salt is Na plus and C2H3O2 minus, and water. This is stoichiometry. So I have 0.0557 molar of the weak acid and the strong base. I have no products because the reaction hasn't happened yet. When the reaction happens, notice how acetic acid and sodium hydroxide are equal in amounts. They are co-limiting. So these both get used up completely. And I make that much product. Water we can ignore. So notice how after the reaction we have no acetic acid, we have no sodium hydroxide. Neither of these are in the beaker after the neutralization. What we have is the salt. So after neutralization, the salt and the water are what remain in the beaker. Remember that the salt determines the pH. Na plus is neutral. C2H3O2 minus is a weak base. I'm going to ignore Na plus. My focus is on acetate. Well, now this is going to look like what we did before. So now we're going to look at the equilibrium. Because in the beaker, we have acetate and water. Now, water is a liquid, so really water is not going to matter. But it helps because since this is a base, that tells us that it's going to accept a proton, leaving water as hydroxide. Acetate is a base. When you think about the K that represents this equilibrium, this will be Kb. And so since it's acetate that is in the beaker, this is what will determine the pH. We'll go ahead and do a calculation with equilibrium. So we'll use an ice table. We had 0.0557 molar. Water we ignore. We had 0 acetic acid and 0 hydroxide after the neutralization because at the equivalence point, those are gone. So now it becomes an equilibrium problem again. So again, here's where, if you look at the problem, even if they give you Ka, they might not give you Kb. On the equation sheet, you have Ka times Kb equals Kw. And on the equation sheet, it tells you that Kw is 1 times 10 to the negative 14. We know from before, at the very beginning of this problem, Ka was 1.8 times 10 to the negative 5th. Because we're looking for the Kb of the conjugate base, we can use Ka times Kb equals Kw. So Kb is 5.56 times 10 to the negative 10. And now we can go through and do the calculation. So Kb is products over reactants. I can assume X is small. By assuming X is small, we can ignore that minus X. I get X equal to 5.56 times 10 to the negative 6th. And look back at the ice table and see what was X that might help us. I see that X was OH minus. So taking the negative log of the OH minus concentration will give us POH. And then subtracting from 14 will give us the pH. So at the equivalence point, the pH is above 7. So calculating the pH at the equivalence point can just take a little bit of time because you're thinking about how are the molarities changing. So you have to go through dilution, stoichiometry, equilibrium. Whenever you have a neutralization reaction, and the pH at the equivalence point is neutralization. So the next question says, sketch the titration curve. Okay, so now we're going to look at the titration curve. So titration curve. So again, with the titration curve, let's start with our y-axis is pH. Our x-axis is volume of NaOH added, because NaOH is what was in the burette. So we calculated the initial pH. It was a while ago, but we calculated the initial pH. The initial pH was 2.866. The initial pH was 2.866. That was the first thing we calculated. I'm just going to draw kind of a general curve. So because it's a weak acid to start, we have that buffer region. So we have this little curve up, and then we kind of have the spike in pH. So This shows my volume at the equivalence point. pH is about halfway up the spike. So we just calculated the pH at the equivalence point. 8.745. The problem told us the volume of NaOH that was added. The problem told us it took 25 milliliters of NaOH to get there. Now we also can figure out then half of 25 is 12.5. Half the volume to the equivalence point is the half equivalence point. Remember, the importance of the half equivalence point is that pH equals pKa. Well, if the Ka of acetic acid is 1.8 times 10 to the negative fifth, take the negative log of that to get the pKa. So the pKa is 4.74. So the pH at the half equivalence point is 4.74. So we have initial pH, we can figure out the pH at the half equivalence point, and we calculated the pH at the equivalence point. We knew the volume of NaOH at the equivalence point, so we know the volume at the half equivalence point. And then lastly, it says to pick an indicator. So again, thinking about indicators. So remember that we need the pH range to encompass the pH at the equivalence point. The pH range of an indicator is pKa plus or minus 1. So we would find the indicator that has a pKa closest to the pH. Just like before, phenolphthalein has a range of 8 to 10. You would be given a list like in the examples. But for us, phenolphthalein would be the best. You're actually going to use phenolphthalein in the titrations that you do on Thursday.